All right, guys, in my spare time, I've been kind of perusing some Regents exams, and I just wanted to make you aware of a few vocabulary words we didn't get to go over this year, but they've occasionally popped up on the Regents exam. They're not hard, and they won't be the focus of the exam, but occasionally you get a multiple choice question on them, and I don't want you to be taken aback by the word. So, for example, here's my first word, invariant. Invariant. Okay? Variant is like variable, something that changes. Okay? When you put in front of a word, for example, insubordinate is a kid who does not listen to me. In, as a prefix, means does not. Okay? So invariant is something that does not change. That's what the word means. And that's all it means. Invariant means something that doesn't change. For example, the fact that I have no hair is invariant. That's not going to change. All right, so for example, trapezoid QRST is graphed on the set of axes below. Under which transformation will there be no invariant points? Invariant points would mean points that don't change. So these are points that don't change. And I want the transformation to have no invariant points, meaning no points that don't change, meaning all the points have to change. So let's go through this. A reflection over the line y equals 0. Well, y equals 0 is a lazy line at height 0, so that's just the x-axis. So y equals 0 is just the x-axis. So I reflect r over the x-axis. R is at 0, 4 here. R will become, I'm sorry, over the x-axis rather. R is at 0, 4. That's going to become 0, negative 4. So here's r prime. S prime is on the x-axis. S is on the x-axis, so S prime won't change. Q is at 3, 3, so that'll become 3, negative 3 if we flip it over. And T prime is here, so that'll go there. And here is my new quadrilateral. As you can see, S did not move. So S was invariant. It didn't change. So this transformation has an invariant point. So this choice is gone. Okay? S was invariant. I want no invariant points. Okay? All right, next up. Our next transformation is going to be reflection over the line x equals 0. X equals 0 is an excited line at 0. It's just another name for the y-axis. So again, r is on the y-axis, so r prime will be on the y-axis. And I can even see at this point, r prime being on the y-axis is invariant. I want no invariant points. This is gone because r will be invariant. Okay. This r 0, 0 is a point reflection through the origin. Little r is a reflection. 0, 0 is through the origin. So if I reflect all these points through the origin, okay, they're all going to go somewhere. R is going to become r prime. R prime is going to be down here. S is going to go through the origin and become S prime here. Q is 3 over and 3 up, so it's going to go backwards that many units in both directions through the origin. So here's Q prime. And T prime is going down 1 to the right, to the left 4 through the origin. So it's going to come out the other side over here. All the points moved. Everything moved. So this had no invariant points. All the points moved. And so none of the points were invariant. Therefore, they all moved, and that would be our answer. Just to go through choice 4, the reflection of the line y equals x. Y equals x is the diagonal through the middle of your grid, basically. Okay, that's where all the y's equal all the x's. And as you can see, Q is actually on that line. So when you reflect Q over the line, Q will remain invariant. And so the answer here would be choice 3. That's a hard question, even if you know what the word invariant means, because you got to go through the choices. All right, here's another one. This was August 2012, number 2. It says the vertices of parallelogram ABCD are A, which was 2, 0. So here's A, 2, 0. B, which was 0, negative 3. C, which was 3, negative 3. And D, which was 5, 0. and there's D. Okay? If ABCD is reflected over the x-axis, how many vertices remain invariant? Again, invariant means does not change. So how many vertices do not change is what they're asking. Well, if I'm reflecting over the x-axis, the ones that are on the x-axis won't change. So A and D are going to remain where they are, and B and C will be reflected over the x-axis. So B will become here as B prime. C will come here as C prime. So two vertices are invariant. They did not change their location. And B prime and C prime were not invariant. Or they were variant, if you want to play with the English there. Invariant vertices, two were invariant. They did not change. Okay. Another word now this word we've actually talked about quite a bit. The centroid is the intersection of all the medians. Okay? Medians, okay, connect midpoints to opposite vertices in a triangle. And you know this, or should know it. Midpoints to opposite vertices. Midpoint to vertex, midpoint to vertex, midpoint to vertex. And the centroid is where they all meet. That's called the centroid. Okay? This first triangle was acute. This first triangle was acute. And notice the centroid is inside the triangle. The second triangle is obtuse. And I'll draw the medians in. Midpoint to vertex as a median. Midpoint to vertex as a median. Midpoint to vertex is a median. And in the middle is my centroid. That's my centroid. And you know that word. Now, we can do this with other things in the triangle. So for example, the incenter is the intersection of the angle bisectors. And if I look at the second letter of each word, okay, I get I and N, and that's how you can remember the word incenter. And these words come up occasionally on the Regents. I'm talking about almost rarely, but I do want you to be aware of them. The incenter is the intersection of all the angle bisectors. So if I try to draw an angle bisector, okay, I'm going to try to draw this one from here. An angle bisector, I want to draw it so that these angles are equal, okay? And so I'm going to try to draw this one so that the angles here are equal, okay? And if I look at this intersection point and go backwards from it, I'll notice that these angles are actually equal. So all the angle bisectors meet at what's called the incenter, which, believe it or not, is different than the centroid. If you can take a look, this centroid is a little to the left of the incenter. Okay? This also can work for obtuse triangles. If I try to draw the angle bisector, again, I'm not drawing it to a midpoint. I'm drawing it so it bisects these angles. That didn't do so well. I want to draw that again. And again, I'm not being particularly accurate here, or I'm just trying to eyeball it. That's pretty good. Okay? And notice, it doesn't go to the midpoint. This line segment is much shorter than this one. Okay? So it's different than the median. The angle bisector is different than the median, and the incenter is different than the centroid. So I'm going to try to draw this one as best as I can. Okay? And here you can really see it, that clearly this blue line segment is not hitting the midpoint of the opposite side. And thirdly, if I bisect this other angle, notice, if I bisect this other angle, that green line segment hits where the other two intersect, and that's called the incenter. And again, that comes from angle bisectors. That's how you can remember the word. Feel free to come up with your own mnemonic devices. I tried thinking about this for about 3 or 4 years, and I can't seem to come up with anything better. But you can come up with your own. The circumcenter is the intersection of the perpendicular bisectors of the sides of a triangle. Now, this one's a little different. So perpendicular bisectors, okay? They have to be perpendicular, and they have to go through the midpoint. So I'm not going to connect to a vertex necessarily. So for example, here's one perpendicular bisector. It's bisecting and we have perpendicularity. Here's another one, okay? It's bisecting and we have perpendicularity. Here's my third one. We're bisecting and we have perpendicularity. And look at that. Okay? They meet again. And this is called the circumcenter. Okay? Now, watch what happens when we do it to the obtuse triangle. This is interesting. So this was an acute triangle. All right, the circumcenter is in that triangle. Now, the other triangle here I have is obtuse, and watch what happens. Here's my perpendicular bisector of my first segment. I'm going to move that over a little bit. Pretty good. Here's my perpendicular bisector of my first segment. Here's my perpendicular bisector of my second segment. I'm going to estimate midpoint right here and draw perpendicular bisector. And notice they're meeting outside of the triangle. Okay? And this can actually happen if I actually draw a perpendicular from this third side that I have here, a perpendicular bisector. It goes right through again. Okay, here are my right angles and here is my bisector. And they actually meet outside the triangle. So my circumcenter here is outside the triangle. Okay, so in an obtuse triangle, and here's something we need to remember. In an obtuse triangle, the circumcenter can be out, or is rather, for an obtuse triangle, is outside the triangle. Now, by the way, the reason why it's called the circumcenter is the following. If I think about this point is on the perpendicular bisector of all three segments, which essentially means that it's the center of a circle that has the vertices of the triangle on it. So let me try to demonstrate. By the way, if you're wondering why it's called the circumcenter, this is why. This is actually, this point here is actually the center of a circle with all three of the vertices of the triangle on it. I'm going to try to draw it. It's a little tough. Okay? Not too bad, though. Okay? And that's why it's called the circumcenter. It's the circle that it's the center that you can draw the circle around that has all three vertices on the triangle. Okay? And again, this stuff comes up very little on the regions, but I do want you to be aware of these terms and where they kind of come from. All right, one more we're going to do. It's called the orthocenter, and that's the intersection of the altitudes. And here's how you can remember the word alto. Okay? The altitudes, that's the orthocenter. That's just a mnemonic device to remember. Okay, so in an acute triangle, my altitude I draw from my vertex down so it's perpendicular. Okay? From my vertex across so that it's perpendicular to this line. Something like this would work. That would be my altitude. That's what an altitude is. And last but not least, I'm going to take this guy and draw, and voila, I'm perpendicular. This guy is called, this point is called the orthocenter. Ortho is a Greek prefix meaning perpendicular. Not that you need to know that so much, but again, alto, that's your orthocenter. All right, that happens in an acute triangle. In an obtuse triangle, it's a little weird. So, for example, an altitude, if you looked, for example, if I wanted to draw an altitude from this vertex to the opposite side, I wouldn't be able to do it because if I try to draw any line segment to this side, it's never going to be perpendicular. So the solution that we have to this is we extend out this side. Okay, we extend it, and then I can drop an altitude or a height down. Okay? And that would be my altitude. And I may have to do that on some of the other segments, or I may not have to. So for example, here, If I try drawing anything across this way, I'm never going to hit perpendicularity. So I'm going to, and actually before I do this, I'm going to extend my altitude here. I'm going to have to extend this side as well so that I can actually draw my altitude. Okay, and as you see, I have to actually extend the other altitude to get an intersection point. So let me redo that because I feel like I'm probably confusing people. So first thing I'm going to do is I'm going to extend this side. And then I'm going to draw my altitude. And they're going to intersect down here. And then the third altitude is one we can actually easily draw. From here, I can go perpendicular to the opposite side without extending. And then if you notice, if I extend this down, they'll hit. There's my orthocenter. Okay? And that thing is outside the triangle. So in an obtuse triangle, the orthocenter is outside the triangle. You can imagine why I kind of kept this to the way end of the course, because there's a lot going on here, but you don't need to know a lot for the regions. Here's what you need to know. Okay, I'm going to summarize it up. For you. The centroid, you know, that's the intersection of the medians. You already know this one. It's always in the triangle. It's always in the triangle. The incenter is always in the triangle. It's the intersection of the angle bisectors. And here's how you can remember. Angle bisectors, my second letters of each word have spell in. Okay? And again, you might think these are stupid ways to remember these, but I racked my head for hours and hours and hours trying to come up with something better, but I can't. Okay. Circumcenter is the intersection of the perpendicular bisectors. It would be inside an acute triangle and outside an obtuse triangle. The orthocenter is the intersection of the altitudes. You can remember this by the word alto. The altitudes meet at the orthocenter. And it's going to be inside an acute triangle and outside an obtuse triangle. And again, these things don't come up on the Regents a lot, but they do occasionally. And I haven't, again, like I've said, I haven't seen a lot of questions on the Regents. In fact, all seven practice Regents you didn't really come up. So as you can see, it's a very small topic, and that's why I kind of want to show you in a video lesson. All right, well, a couple of Regents questions. This was the fall 2008 sampler number 25. In which triangle did three altitudes intersect outside the triangle? So outside the triangle intersection, that's an obtuse triangle. Okay? And we just saw why. Obtuse triangle, choice 3. August 2012, number 24. For a triangle, which 2 points of concurrence could be located outside the triangle? Well, and outside the triangle would be an obtuse triangle. And this can only happen, it doesn't happen with the centroid. So here are your 4 choices. And you can get these from the reading. Centroid, incenter, circumcenter, and orthocenter. Centroid, we know, is always inside the triangle. It's the center of gravity. Okay, if you remember when I gave you the cardboard cutouts, the centroid is the center of gravity. So the center of gravity of something, in order to balance it on your finger, the triangle, the center can't be outside the triangle. The incenter is always in the triangle. And so it's the circumcenter and the orthocenter that can be outside in obtuse triangles. And so the answer is choice 3. Okay, one more. January 2012, number 2. In a given triangle, the point of intersection of the 3 medians is the same as the point of intersection of the 3 altitudes. Which classification of the triangle is correct? Well, we can kind of go through these and try to draw them out. So for example, I have a scalene triangle. Okay, here's a scalene triangle. All 3 sides are different. All right, now let me draw my medians in. So my medians go from midpoint to vertex, midpoint to vertex, midpoint to vertex. There's my centroid. And actually, I'm going to do this again because I want to make this triangle a little bigger. So here's my scalene triangle. Sorry, I'm going to do this again, make it a little bigger. Here's my midpoint to vertex, midpoint to vertex, midpoint to vertex. There's my centroid. Okay? Now the intersection of the altitudes. Intersection of the altitudes. Altitudes go from vertex, but make a right angle at the bottom. Now, I don't need to draw all three in to clearly see the centroid is not going to be on this perpendicular, this altitude. So they're not going to intersect at the same place in a scalene triangle. Okay? Now let's try with an isosceles triangle. Let's try it with an isosceles triangle. So here's my best rendition of an isosceles triangle. All right, my intersection of medians. Midpoint to vertex is a median. Midpoint to vertex is another median. Midpoint to vertex is my third median. There's my centroid. Now we're going to do altitudes. In an isosceles triangle, the altitude is the same, actually, as for going down to the base. The altitude is the same as the median, but it's not the same from the other sides because the altitude has to be perpendicular, and here, and if you see there's a slight difference here, if I'm trying to draw something that's perpendicular, I'm going to have to draw it a little lower, believe it or not, okay, to get a perfectly good right angle. So my orthocenter is here. So this doesn't work in an isosceles triangle. I'm actually going to show you a little bit more of an extreme version. If you make the isosceles triangle even more extreme, you'll see it a little more clearly. So if we make it like this, you'll see it more clearly. Here's my midpoint down to my vertex. Here's my midpoint down to my vertex. Here's my third, and that would be my centroid. So that would be the centroid. Now, clearly, this is not a right angle. I would need to shift this much further down to get a right angle, okay? Shift this much further down to get a right angle, but this guy actually gives me a right angle. But clearly, the centroid and the orthocenter are not the same. Okay, next up, equilateral triangle. So I'm going to throw this one away. Get rid of you. I'll cut you out of here. Cut. And here is my equilateral triangle. And now a thing of beauty is going to happen. I'm going to have my midpoint. I'm going to make my centroid first. Midpoint to a vertex. Whoops. Sorry. Midpoint to a vertex. Midpoint to a vertex. Midpoint to a vertex. There's my centroid. Now, if we notice something, all of these sides are actually also altitudes because they all end up being perpendicular. So in the equilateral triangle, all the altitudes are the same as the medians for all three sides, not just for the one coming down from the vertex. Okay? And number 4, get rid of this guy. And number 4 is a right isosceles triangle, which looks like this. Okay? Here's my right isosceles triangle. My medians, okay, midpoint to vertex, midpoint to vertex, midpoint to vertex. There's my centroid. Now my altitudes are interesting here, okay? I need to go from the opposite side to get perpendicular. Well, the only way that's going to happen is if I actually draw the side itself. This is an altitude, it's a height. This is an altitude, it's a height, okay? And actually, this is also an altitude, it's a height. They're going to meet right here. That forms the orthocenter, okay? And so that would be out. They're not, the orthocenter and the centroid are not the same thing. Don't worry if you're totally confused by these questions. They're a little tricky, but I just wanted to give you a little bit of a video to go over them. Feel free to come in tomorrow. I'm going to text you guys when I'm available tomorrow. if you have any questions for me. Okay? Again, these are little things on the regents that, quite frankly, I don't think they're worth spending 3 or 4 or 5 days on in class. I'd rather have you spend more time on other things that pop up a lot more often. But I also didn't want you to be totally unprepared for questions like these.